All right, so we're recording. All right, so again, back to this conservation of mass problem. Sorry that the internet went out there. Again, so when you're presented with this as a word problem, you're going to be given the chemical equation. Write the masses of the chemicals right underneath. Okay, it's amazing how many people don't follow that simple bit of advice and end up getting what amounts to just a simple addition or subtraction problem, getting it wrong. It's amazing how many people get this wrong. Right, I'll do one more here. So you're going to get an assignment that has two of these. Okay, any question before I erase this? Okay, again, since we're restarting the video here, we were giving the original chemical equation in black, and we were told that 46 grams of sodium metal reacts with 71 grams of chlorine gas to give us some unknown amount of sodium chloride salt. Okay, so we just add the two numbers together, solve for x, we get x is 117 grams. And we said that the left-hand side of a chemical equation is called the reactants. They are what you start out with, and the right-hand side, what you end up with, are the products. The products are produced. The products are produced. Okay, again, an egg, flour, chocolate chip cookies. Okay, any questions there? Any questions? All right, so I'll do another one here. And let's look at, so we'll burn some propane here. 2 plus H2O. And let's see here. So 4, 3, and 5. Okay, so this is the chemical reaction for the combustion of propane gas. Okay, and we'll say, let's say that we have 160 grams of oxygen gas are used to produce 72 grams of water, right? 72 grams of water, and let's say that we burned 44 grams of propane, and we want to know how many grams of carbon dioxide are produced. I mean, this is a pertinent problem nowadays with all this talk about global warming. Okay, so again, 44 grams of propane react with 160 grams, are burned in the presence of 160 grams of molecular oxygen to produce 72 grams of water vapor and some unknown amount of carbon dioxide gas. So we're going to bring down our plus signs here, and we're going to solve for x. Okay, well, let's see. 72 is being added to x, so I'm going to subtract 72 from both sides. Subtract 72 from both sides. So there we go. So what does x equal? Actually, we said we were going to put an equal sign here. Okay, so let's see. That's 204 minus 72. And I'm too tired to do it in my head. So I see 132 grams. So we get 132 grams of carbon dioxide gas out whenever we burn 44 grams of propane. Okay? And we can see that why global warming is such a problem. You get 3 times as much carbon dioxide gas out that gets released into the atmosphere as the propane that you burn. Right? So this is why the burning of fossil fuels is such a problem. We'll find out later in the course that this exact same equation with different numbers here, of course, but the exact same chemicals, if let's see here. I had a butane lighter here on the table a few minutes ago, but if I could replace the propane with butane, and the rest of the chemical reaction would be exactly the same. You're burning octane in gasoline, the exact same. We replace C3H8 with C8H18, right? But we still have oxygen gas and carbon dioxide and water vapor. Okay? So any questions there? Should I do, what are the reactants here? What are the reactants? The C3H8 and the O2. The O2. Can I erase this on the bottom in here? Can I erase this on the bottom? Everybody?
Yes.
Okay, so when you were asked on this assignment, what are the reactants? Don't write carbon and hydrogen and oxygen. Those are not the reactants. Okay, the reactants are the compounds. So what are the compounds? Well, I see C3H8, that's one of them. And the other one is O2, not 5O2, but O2, right? The 5 just tells us how many O2s we have, right? So these are the reactants, and they get turned into the products. So what are the products? Carbon dioxide, CO2, and water vapor, right? Reactants and products. Does everybody see that? Okay, remember, the products are produced. Okay, do we need to do another one of these?
Yes, please.
All right, one more? Okay. Any other questions while this is up here? Any other questions? All right. Let's look at, I'm going to have to probably grab my periodic table for this one. Let's look at let's see, plus, yeah, let's make it this. Plus calcium fluoride gives us, let's see here. Let's see, we're going to need 3 of these, and that's going to give us 6 NaF plus Ca3, PO4, and 2 of those. Ca3, PO4, 2, calcium phosphate. Okay, now let's get some numbers in here. I'm going to have to do this on the calculator here. All right, so suppose, I'm just going to go use the formula weights here. So suppose we have 330 grams of this, 330 grams of that, okay? And let's see here. And 234 grams of this, calcium fluoride. All right, I'm going to put the plus sign there. We bring down the arrow, turn it into an equal sign. Sodium fluoride, where do we find sodium fluoride in everyday life? Hopefully, where do we find sodium fluoride at? Hello? Nobody knows?
Toothpaste.
Toothpaste, correct, very good. It's in toothpaste. It's a very small amount of it, but it is there. All right, and we get 252 grams of the sodium fluoride and some unknown amount of calcium phosphate. Now, we'll do this later in the course, but it's good to wet our beak a little bit right now. This will dissolve in water. This will dissolve in water. You mix the two together. Remember when I did that on Monday, the last experiment on Monday? I had 2 clear solutions, mixed them together, and we formed a solid. Creation of a new solid told us it was a chemical change. This will form a solid. This stays dissolved. So stays in solution, stays in solution, stays in solution, forms a solid. Right? So how much solid will we get out here? How much solid will we get out? Okay? Well, we got to solve for x here. 252 is being added to x, so I'm going to subtract 252 from both sides. Right? So I'm going to subtract 252 here. That cancels, and we're left with x equals, so we get out our little calculator here. So 330 minus 252 equals plus 234. And I get 312 grams of calcium phosphate. 312 grams of calcium phosphate. Okay? So conservation of matter. Right? The total mass of the reactants equals the total mass of the products. The total mass of the reactants equals the total mass of the products. Now, another question you're going to be asked here on this assignment. What's written in black there? Is that a physical change or a chemical change?
Chemical.
Maybe
How do you know?
because it forms a new solid.
Yes. Remember that in a physical change, the fundamental composition of the substances stays the same. Okay, here I have sodium phosphate. I don't see sodium phosphate over there. So that clearly tells me this is a chemical change. A chemical change. Okay, now, and again, you should be able to recognize that without knowing that that forms a solid. Because right now, at this point in the course, you don't know that that's going to form a solid and these other three stay in solution. You're just going to be presented with the equation in black. And you're going to be asked, is it a chemical change or a physical change? And we'll give an example of a chemical change, or sorry, a physical change here in a moment. But everyone has what's in red here. Okay, so let's identify what the reactants are and what the products are. All right, so the products, let's go to blue. The products are NAF, and the calcium phosphate are the products. All right, what are the reactants? Okay, we don't worry about the 6. What are the reactants?
The sodium phosphate and calcium chloride.
Right, Na3PO4 and CaF2 are the reactants. Okay, so you're going to be asked that. And that's it. That's all there is. Right? We're already spending way too much time on this for as simple as a problem as it is. I said I would write something up here that was an example of a physical change here. Okay? Everybody have this? I can erase it. All
Yeah.
right. I'm going to leave the black chemical equation up there. But let's take a look at, let's see, we talked about sublimation on Monday. And we should know that carbon dioxide gas, solid is dry ice, called dry ice. Okay, and we can let that warm up and it's going to disappear, and it's not going to turn into carbon dioxide liquid, but carbon dioxide, carbon dioxide gas. Carbon dioxide gas. So this is sublimation, where a substance goes straight from the solid state to the vapor or gaseous state. Okay, so here, this is clearly a physical change. The chemical formula of the reactant is identical to the chemical formula of the product. It has just changed its physical state or appearance, right? That's a physical change. That's a physical change, okay? But again, if I have 100 grams of the solid, I end up with 100 grams of carbon dioxide gas, okay? Conservation of mass, conservation of mass. In any physical or chemical change or process, the total amount of the matter stays the same, or the total mass remains constant throughout the change. The total amount of mass before in the reactants equals the total amount of mass in the products. All right, any other questions or comments? Any other questions or comments? This is very, very simple. Very simple. So you get 2 problems like this. I mean, you should be able to do them in just like 3 or 4 minutes. Okay, now that brings us to the second half of the chapter, which is energy. Energy. And so why does our textbook put matter and energy into the same chapter? On the surface, they might seem quite different. When in reality, they're actually I like to think of them as first cousins to each other. All right, and if I were asked to ask the class, what's the most famous equation in all of science? What would you say? Somebody volunteer to answer that. Most famous equation in all of science.
Squared.
Louder?
E equals mc squared.
E equals mc squared. All right, I'm glad you said that. Sometimes people say F equals ma, Newton's second law. Who first came up with this equation?
Wasn't it Einstein?
Einstein. Wrong. Some Italian guy that gets no credit. Gets no credit. He came up with it a few years before Einstein. But Einstein derived it in special relativity. I'm not sure. I don't remember the context in which the Italian guy came up with it. Okay, but no one ever talks about the Italian guy. Okay, so if we take a look here, the M is mass and the E is energy, right? So we can interconvert back and forth between the two, right? So this is why I say matter and energy can be thought of as first cousins to each other, right? Some people would just say they're the exact same thing. They're just manifested differently, right? They're just manifested differently. What's C in that equation?
You said what's the C?
C. What is C in this equation?
Isn't it a constant for like the speed of light or something like that?
Yes, it's the speed of light, which is a very big number. The speed of light is 300 million meters. 300 million meters. So you square it, right? 3 times 10 to the 8th becomes 9 times 10 to the 16th. So this is a very big number. So this is telling us a small amount of matter can generate an enormous amount of energy. Hence, atomic and nuclear bombs. Right? Take a small amount, a few kilograms of plutonium, and you can level a large city. Because that mass multiplied by the speed of light squared generates an enormous amount of energy. Right? So why did I bother even to mention that? Again, because that shows that the two are interconnected with each other. One can be turned into the other. All right, so what is energy then? What is energy? Very simply, there's a lot of definitions in this chapter, in both the matter part and the energy part. Energy is the ability to do work. The ability to do work. All right? If you don't, now, which brings us to what is work? What is work? Now, these definitions are right out of your books. If you have the book, it's up to you whether or not you want to write them down. It's probably a good idea, though. Right, so
We didn't get what you said, Raymond. Your video cut out again.
Okay, energy is the ability to do work. The ability to do work. All right? Which begs the question, what is work? All right, work is one of the, in everyday life, is probably one of the more misused words. Okay? There's a lot of words that have very strict scientific meanings, but they're co-opted in everyday life in a completely different manner. I'm going to work. Well, in scientific terms, that means absolutely nothing. So what is work? Work is the application of a force through a distance. The application of a force through a distance. Okay? Application of a force through a distance. All right, so energy, the ability to do work, application of a force through a distance. Now, let's just take a moment to discuss this in a little bit more detail. Okay, it takes energy to do work. Right? When you do work, you're expending energy. Okay? Now, we said that work was the application of a force through a distance. So think about this for a moment. Usually I'm in the classroom and I can push on a wall. I can't really do that here. Okay? But suppose your car breaks down on the road and you're the only one there and you're trying to push it. You can't, you're not strong enough to push the car. Guess what? It could be, you could be sweating your butt off, veins bulging out of your head. If that car does not move, you have done zero work. You have done zero work. The car hasn't moved. Application of a force, well, yeah, you're pushing on a car. That's application of a force through a distance. Through a distance. But so you're pushing, but not through a distance. So zero work has been done. Zero work has been done. Right? So we understand this scientific definition of work. Right? Scientific definition of work. All right? Now, since there's no questions there, how about what are standard units? What's the standard unit for energy? Right? And our book actually mentions several units for energy. And one is, the standard unit is what's called the joule. All right? So like the standard unit for time is seconds, standard unit for mass is kilograms, standard unit for energy is a joule. A joule, J-O-U-L, named after a French scientist. Okay, but our book also mentions a couple other units, and I'm going to mention two here. We have the calorie, the scientific calorie. All right, and we also have this calorie with the capital C. So lowercase c for the scientific, uppercase C for the nutritional calorie. Nutritional calorie. Okay, so when you say, oh, you know, that don't eat that burger, it's 1,200 calories. You're talking about this one. This one. Okay, this one here, the scientific calorie, is pretty much not used anymore. I'm so old that I can remember chemistry textbooks back in those days. Actually, when they talked about energy, a lot of them used the scientific calorie. But it seems nowadays, the general chemistry book that I use uses everything is in joules. Calories is never mentioned in the book. Never mentioned. Everything is in joules nowadays. Okay, which is probably a good thing. It is the standard unit. Okay, what's the connection between the scientific calorie and the nutritional calorie? Well, write it down here. 1,000 scientific calories, and yeah, we can see that. 1,000 scientific calories equals 1 nutritional calorie. Right? 1,000 scientific. So in other words, the nutritional calorie is a kilocalorie of scientific calories. Right? So 1 kilocalorie of scientific calories equals 1 nutritional calorie. Sometimes it might be better if nutritionists use the scientific calorie, because you know, if you go buy a candy bar and it says, oh, there's 700 calories in this candy bar. You think no big deal, 700 calories, I can handle that. But if that wrapper said this candy bar has 700,000 calories, you might think twice before you ate that, right? But it is what it is. There's actually one other unit for energy that's used in everyday life. Can anybody think of one? Anybody own a house here?
Kilowatt.
Kilowatt. No, kilowatt is power. Kilowatt is power. But you're close, whoever said that.
Isn't it volt?
No, volt measures electric potential difference. It is the kilowatt times hour, kilowatt hour. Right? And about the only time you see that is when you get your electric bill. That's about the only time you ever see that, is when you get your electric bill. Right? I've never seen it anywhere else. So when the meter maid comes around to read the meter, electric meter at your house, the unit they're reading is kilowatt hours. Okay? So why do they use kilowatt hours instead of joules? Because if that meter read joules, your monthly electric bill would be in like tens of millions of joules. I can't remember off the top of my head. It's something like 93 million joules equals 1 kilowatt hour, or 9.3 million joules equals 1 kilowatt hour. I always forget it off the top of my head. I recalculate it every year and then forget it. Okay, so again, it's much easier that if you get your electric bill and it says you've used a few hundred or a few thousand rather than tens of millions of joules. And this is why the electric company uses that. Okay? Any other question? Again, we like to use, believe we've talked about this before, we like to use numbers that are relatively small, right? Once numbers get really big or real small, it's tough for human mind to comprehend them. All right, so there's our 4 units. Again, the joule is the standard unit. And remember, it's not kilowatt, it's kilowatt hour. Kilowatts measures power, okay? Power. So when you go buy a light bulb, a 100-watt light bulb, that's a rating for power, not for energy, not for energy, all right? Okay, any other questions here? Any other questions?
No.
All right, then let's move on. I want to mention here that let's look at some different types of energy. Different types of energy. And I usually spend way too much time talking about this, but here we have energy. And there's 2 main kinds of energy. Anybody know what they are? 2 main types.
Kinetic.
Kinetic and potential energy. Okay, now let's do kinetic first. It's a nice, easy one. Kinetic energy is the energy associated with objects in motion. The energy associated with objects in motion. Okay, and you can easily calculate kinetic energy. Kinetic energy is equal to mv squared over 2. So the mass of an object times its velocity squared divided by 2. Looks a lot like E equals mc squared, right? So the mass of the object times its velocity squared divided by 2, right? So we could take a look at a bullet fired from a gun. Right? Anybody have any idea how fast a bullet moves?
I mean, it kind of depends on the bullet.
Roughly.
About 400 miles an hour.
Yeah. Well, come on, we don't use miles an hour here. It's about 1,000 meters a second, if I remember correctly. About 1,000 meters a second. Okay? So, but think about it. The bullet has a relatively small mass, maybe just 20 or 30 grams. Right? Probably more than that, but it's a small mass. But it's moving really fast. It's moving really fast. So when it hits you, it does some serious damage. All right? On the other hand, we could have a bus. A bus is maybe moving a few tens of meters a second, but it has a much, much larger mass than a bullet does, right? A much, much larger mass. So likewise, when the bus hits you, it also does a lot of damage, but not because it's moving fast, but because it has a big mass. Whereas the bullet is the opposite. It's moving fast, but has a small mass. Okay? So an object at rest, such as, here, my calculator here, I put it there. That calculator right now has 0 kinetic energy. It has mass, but its velocity is 0. So it has 0 kinetic energy. It's not moving. It's not moving. Okay? That's a pretty easy one to understand. Just because I'm in the habit of teaching high school so much, and this video also might be viewed by my high school students, and so I'm always big on vocabulary with them. Kinetic, what is this Greek prefix? It's actually kinos, K-I-N-O-S. What does that mean? Kinos. Okay, actually in order to save time, it means to move, So we can see why it's called kinetic energy. Kinetic energy. All right, now potential energy is a little more complicated. All right, and it's actually 2 parts. So I'm just going to say what it is rather than prompt us. Actually, I have the whole screen there, so I can't see what time it is.
It's 5:25.
Just grabbing my watch. Okay, so I don't think we'll finish this energy today, but we'll come close to it though. All right, so potential energy, right, is definition is in a book, right? Potential energy is, now, before I say what it is, quite often people give the middle school definition. They say, well, this is the energy in motion. This is energy of objects at rest. And that is not true. It is true for kinetic, energy of objects in motion, but this does not mean energy of objects at rest. Right? It's not as simple as that. So what is potential energy? It is energy stored in an object. Stored in an object due to its position or composition. Due to its position or composition. Right? Due to its position or composition. Right? Energy stored in an object due to its position or composition. Now, let's do the position one first. Okay? So quite simple. Here I have a 10 gram or 10 kilogram, 10 kilogram or 10 pound? I think it's 10, it feels like 10 kilogram. All right, so 10 kilogram weight here. Okay? Now, if you were laying on the floor, all right, and I said, I'm going to drop this on your head, would you rather I drop it from way up high or just above your head? Which one would
Just
you
above.
just above your head? Okay, now why is that? Because when this weight has some potential energy due to its position, right? It has more potential energy. The higher it is, the more potential energy it has, right? The more potential energy it has, right? And specifically, the more gravitational potential energy. And gravitational potential energy can be calculated very easily. The mass of the object times the acceleration due to gravity, that's just the weight of the object, okay? mg is the weight of an object, times its height above some reference point, times its height above some reference point. So you always need a reference point when you're talking about potential energy. This is a big difference between kinetic and potential energy. Okay, now I'm going to say something. I don't think this is in our book, but it's something worth mentioning. You cannot measure. It is impossible to measure potential energy. It is impossible to measure potential energy. You can only measure changes in potential energy. You can only measure changes in potential energy. And you must have a reference point for potential energy. You must have a reference point. I guess the reference point for kinetic energy is when the velocity is zero, the object's not moving, right? But you must have some reference point. So I could actually call when the weight is high, I could say that's zero, right? I could say the height is zero, right? And then down on the floor would be some negative height, right? But normally you would pick the ground to be, you would define that to be where the height is zero, right? Normally we would do that, okay? So let's just do this real quick here. So suppose, yeah, we can see that. So here you throw a ball up in the air. You throw a ball up in the air, right? And we can introduce another conservation law here, right? So when you throw the ball up, right? And if we define the ground to be zero, the height is equal to zero at the ground. So you throw the ball up, it has no potential energy there, right? It's at the ground. It has no potential energy. But now the ball starts going higher and higher into the air. And H is getting bigger and bigger. So the gravitational potential energy is getting bigger and bigger and bigger as the ball goes higher and higher into the air. But then it starts to come back down. So H is getting smaller and smaller and smaller. Finally, when it's back on the ground again, the gravitational potential energy is zero because the height above the ground is equal to zero, right? So that's the gravitational potential energy. It gets higher and higher as it goes up, reaches its maximum at its highest point in the air, and then it starts to drop again, okay? The potential energy gets smaller and smaller as it drops. Now, it must have taken some energy to get that ball up into the air, to leave the ground and go up into the air. So remember, as the ball is moving, it now has kinetic energy. as the ball is moving, it now has kinetic energy, right? Actually, here, let's write this down here. So here, when the ball is here, the gravitational potential energy equals 0. And over here, the gravitational potential energy equals a 0, right? And we can say when the ball is at its highest point in the air, so up here, the gravitational potential energy is at its maximum value. Its maximum value, right? Now, you throw this ball in the air, it comes back down. Where is the ball moving the fastest? Where is the ball moving the fastest? In other words, that's going to tell us when V is the biggest, that's like saying, where is the kinetic energy the biggest at? Where's the velocity of the ball the greatest?
Isn't it when you first released it?
Yes, yes, down here on the ground, right? Because it moves slower and slower as it gets higher and higher, right? So down here, the kinetic energy, yeah, you can still see that. The kinetic energy equals a maximum value here, right? And it's going to equal maximum value when it hits the ground on the other side. Kinetic energy equals a maximum value here. Okay? Maximum value there. Where is the ball moving the slowest at in that
Right at
journey?
the peak.
At its peak. What is the velocity up here at its peak? What is the velocity?
Like just before it comes back down?
Yeah,
Wouldn't it be 0?
it's 0. It's 0. Very good. Who said that? Was that Lucas?
Yeah, it was Lucas.
Okay, so here, the kinetic energy is at its maximum value. The kinetic energy is at its maximum value. Oops, sorry. That's where it's at. It's equal to 0 there. It's equal to 0 there. Because the velocity is 0. The velocity is 0, right? It stops moving just for a very short time, right? Very short time. The velocity is actually 0 when the ball is at its highest point in the air. Okay, now let's take a look here. Here, on the ground, the potential energy is 0, whether you're just releasing it or it's coming back. But the kinetic energy has its largest value at the ground. We have the exact opposite situation up here. At the highest point, the potential energy is the maximum value because the height above the ground is the highest. Remember, gravitational potential energy is mass times acceleration due to gravity times height. But the kinetic energy is as its smallest value, 0 there, right? So there's some relationship between those two. Anybody have any idea what that might be?
When kinetic energy is at its maximum, the potential energy is at its 0.
Well, that's true, but I'm after something else. The total amount of energy, no matter where the ball is at, the total amount of energy remains constant. No matter where the ball is at, the total amount of energy remains constant. So in other words, looking for another color marker here. So when it's halfway up, let's suppose that's halfway, the energy is half kinetic and half potential. Over here, it's half kinetic and half potential, right? When it's 1/4 of the way up, the energy is 3/4 kinetic and 1/4 potential, right? So you can very easily calculate the energy anywhere in the journey of the ball. You can very easily calculate it. You can even figure out how fast the ball is moving. I mean, right here, when it's halfway, you can very easily calculate. If you take physics, you'll be given that problem. Okay, I've drawn this as a projectile motion problem. You'll be asked, how fast is the ball moving halfway up? Right? Well, you know that what the total amount of energy was at the beginning, and so you know that halfway up, half of the energy is potential and half is kinetic. Okay, let's see. Somebody's waiting for me to admit them. Okay, I don't know why I have to do that anymore. All right. Sorry about that, Miss Jasmine. Okay. All right, I just want to mention one last thing here, okay? Which is, why is the velocity 0 there? Anytime an object reverses direction. Now, here I'm talking about reversing direction in the vertical direction. So in the vertical direction, it's going up, and then once it reaches its maximum height in the vertical direction, it begins to come back down. All right, so we're talking about, in this case, reversing direction in the vertical direction. Anytime an object reverses direction, for a split second, its velocity is 0. For a split second, its velocity must be 0 when it changes direction. Okay? All right, so that's potential energy due to position. We can also think of, here, let's look at another example here. Any question while I have this up here? Any question? All right, let's look at another example here. Another example.
So what was the definition? Any object reverses.
No, it's just that the velocity will be 0 for a split second when an object reverses direction. So here's a box sitting on the floor. All right, and here we have a spring. All right, and the spring is compressed. All right, what happens when I release? Okay, so I'm holding the box. What happens when I release the box? The spring is compressed initially.
The spring is going to push the box.
Right, the spring is going to push the box in this direction. Well, we know it takes energy to move that box. It takes energy to move that box. Where did the energy come from? From the spring. Okay, the spring is compressed. It has stored potential energy in it. Now, that's not gravitational energy. That's stored mechanical energy, right? And you could very easily calculate, if you take physics, there's a very simple equation to calculate the energy stored in the spring. We don't need to get into that, though. But I will tell you, it's almost, for spring motion, chemists used to a first approximation the exact same equation for the energies stored in chemical bonds, for the energy stored in chemical bonds. Okay, so again, this is another example of potential energy stored in an object due to its position, right? You release the spring, or you release the box, the spring expands, and it's, we can think of it as having changed position, that energy gets released, all right? Now, any question there? There's many other examples, but I think the two we did is sufficient. Now, how about the other half of the potential energy definition, which is energy stored due to composition or arrangement of particles in an object or matter? Okay, well, they're a very, very simple example. Okay, think of, okay, we had propane up here before. So why do we use propane as a fuel? Because it has a lot of energy stored in the molecules. Stored in the molecules are chemical bonds, right? So anything that we utilize as a fuel, F-U-E-L, any compound that we use as a fuel, propane, kerosene, gasoline, wood, they have a lot of stored potential energy stored in the molecules or chemical bonds. In particular, we call it stored chemical energy. Chemical energy is the energy stored in chemical bonds. Energy stored in chemical bonds. Okay? Stored in chemical bonds. Now, you know, usually, I'm going to just say this real quick here because we're almost running out of time here. Gravitational potential energy is the reason that we build dams on rivers, right? It raises the height of the water. And actually, you know, it's worth mentioning this. The water level rises. So the water behind the dam gets greater and greater gravitational potential energy the higher it gets. Okay, well, usually on the other side of the dam is some hydroelectric plant, right, which is going to produce electricity, right? So the water comes down, and as the water drops, it's losing gravitational potential energy, but it's gaining kinetic energy, right? Just like the ball. So the energy is being converted from potential to kinetic as the water drops. And then down at the bottom, it hits turbine blades and spins them. So that kinetic energy is converted into mechanical energy, spinning the turbine blades. And those turbine blades, I'm not an expert on this, so I'm not going to pretend, but that's connected to some electric motor. So it's converted into electricity ultimately. So you have gravitational potential energy converted into kinetic as the water falls, converted into mechanical as the turbine blades spin, ultimately converted into electrical energy, right? And then there's some power lines connected to the hydroelectric plant, which takes it to your house or wherever, okay? But we can see that energy can be transformed from one type into another. Energy can be transformed from one type into another, right? We saw that with the ball being thrown into the air, okay? But we saw that when the ball was being thrown into the air and falling back down, I actually drew that to make this point, and then I forgot to. We said that the total amount of energy is constant. No matter where the ball is in its trajectory, the total amount of energy remains constant, okay? But, so we have, just like we had conservation of mass, we have conservation of energy. And what does the conservation of energy tell us, right? And our book says in any chemical reaction, the total amount of energy remains constant. Well, why limit it to chemical reactions? Why not physical changes also? So we can say in any physical or chemical process, a physical or chemical change, the total amount of energy remains constant, but it may be transformed from one type into another, okay? Maybe a shorter way of saying, again, there's many different ways of saying the conservation of energy, okay? The one I like to use is energy can be transformed from one type into another, but the total amount of energy in any physical or chemical process must remain constant. Energy can be transformed from one type into another, but in any physical or chemical process, the total amount of energy must remain constant. All right, and just like we said, you can't melt an ice cube and have enough water to fill your swimming pool because the conservation of mass tells us that cannot happen. Well, the same thing with conservation of energy. All right, now that it's starting to get a little cool in the mornings, you can't strike one match and expect it to produce enough energy to heat your whole house. Not going to happen. Right? There's some chemical energy stored in that match head. Some chemical energy is stored in that match head. Right? So when you strike it, it gets converted into what's called thermal energy, which we're going to mention here, the very next thing that we talk about, thermal energy. Right? Quite often we refer to it as heat. Right? Although they're not technically exactly the same thing. Right? So again, energy can be transformed from one type into another, but in any physical or chemical process, the total amount of energy must remain constant. Excuse me. All right, so we're almost at the end here, and I just want to mention, we did talk about some different types of energy. All right, again, remember, any fuel, F-U-E-L, has a lot of stored chemical potential energy. All right, actually, let me just run over a few minutes. If we look at, say, any explosive device, so like TNT or dynamite, right? They have a lot, those materials have a lot of stored chemical potential energy in their bonds, right? So any fuel or any explosive has a lot of stored chemical potential energy. Okay, I wanted to mention something like, say, uranium or something, or plutonium, right? That has a lot of stored nuclear potential energy, right? So it's not the same as chemical potential energy. Chemical potential energy is stored in chemical bonds. Nuclear potential energy is stored in the nucleus, right? Stored in the nucleus. I should mention here, it's worth mentioning and quite often overlooked, that every atomic nucleus has a great deal of nuclear potential energy, okay? So even oxygen nucleus does, okay? Now, why do we only use uranium and plutonium? Well, for technological reasons, we're kind of limited to plutonium and uranium in nuclear power plants or nuclear weapons. Okay, and it's because you have to get a sustained chain reaction, and you can't do that with other materials, right? So that's why we're greatly limited in our utilization of nuclear potential energy in everyday life. Okay, but again, there's an awful lot there. The nuclear potential energy compared to chemical potential energy, nuclear potential energy is typically millions of times greater, right? You have a few kilograms of dynamite that might blow up a building. If you have a few kilograms of plutonium or uranium, you can level a large city, right? You can level a large city. Okay, so the amount of nuclear potential energy stored in a given amount of matter is much, much greater than the amount of chemical potential energy stored in that same amount of matter. Okay, so I just have one more thing, and then we'll end this section on energy, which is, what is thermal energy? Thermal energy. What is thermal energy? Okay, and we're given a definition there in our book. It's the energy associated with the random motions of atoms or molecules. The energy associated with the random motions of atoms or molecules. Okay? Energy associated with the random motion of atoms or molecules. All right? Now, let's just talk about that for just a minute. The faster those motions, the greater the amount of thermal energy. The greater the amount of thermal energy. Okay? Now, let's look at an example of this thermal motion, or sorry, thermal energy. All right, when we were talking about states of matter, and we talked about particle motions in solids, liquids, and gases. And we said that in solids, the atoms or molecules are just vibrating about fixed average positions. Right? Well, if those atoms are vibrating, that takes some energy. That's thermal energy. That's thermal energy. Okay? We said in liquids, okay, the liquid molecules are free to roll or slide over each other. They're moving. That takes some energy. That's thermal energy. That is thermal energy. Okay, and we said gas molecules, right, are free to fly around their container. Right? Well, if they're moving, 1/2 mv squared, that takes, so that kinetic energy is thermal energy. So thermal energy is a type of kinetic energy. Thermal energy is a type of kinetic energy. Chemical energy is a type of potential energy. Okay? Do we have any questions or comments? Any questions or comments? Now,
No.
I have a couple of assignments on energy, but I mean, I can send it out so you can get started on it, but there's going to be a couple questions on it that we haven't covered today. We'll cover next class. So don't bother sending it to me. Okay, don't bother sending it to me. I want you to be able to answer these other questions also. All right, maybe sometime I should tweak that assignment so that you can, so I can give you one the first day. So for next class, if you have a book, you should take a look at section 3.9, energy and physical and chemical changes, and then temperature, the next section. All right, so the 3 temperature scales. All right, so we'll see the relationship between thermal energy and temperature. The relationship between thermal energy and temperature. So if you have a book, it's only a couple pages, go ahead and read it. You'll get much more out of our next discussion. Okay? All right, any questions or comments? I'm going to stop recording here.